Let me know when we're live or we're recording there.
All right, we are live and good to go.
Good day, everyone. Welcome to our webinar presentation. My name is Adam Harris, Managing Director for C-Therm Technologies. Very pleased to have you on the line with us today. This is a different webinar format than we've used in the past. We're excited about it. It's got some great new features and greatly helps streamline the process, making it more efficient for you as a participant. We are recording today's feature. It will be uploaded to our website and made available as an archived recording. With me, I have Arya Hakimian. Arya is an application specialist and has a lot of experience running our thermal conductivity measurement under high pressure conditions. Very pleased to have him with us here today to talk a little bit about how we do that and some of the applications where it matters most. Most of these application areas are coming from the oil and gas sector, although there are other scenarios where it can be very important to understand the thermal conductivity of your material at high pressure conditions. We see a lot of interest in the process safety field in general, where in really properly understanding the thermal dynamics of your materials under these types of conditions, it's really important to consider the impact of pressure, as it will have a material difference as to the effective thermal conductivity and the broader heat transfer dynamics of those materials in those conditions. There's also been some really interesting work done by other researchers in representing environments not of this earth. So I think there's an example of an application highlight that mimics, I think, Mars with the use of a high pressure cell. So you can get into some very interesting work with these cells and this really unique capability. There's not a commercial source that we're aware of, alternatively, in combining the high pressure capability with the thermal conductivity measurement itself. So it's something we really pride ourselves on in terms of driving innovation in this space, all with the belief that it's important to really be able to characterize your material under representative conditions. So the title for today's webinar is Measuring Thermal Conductivity Under Pressure, Application Where It Matters. I want to provide a quick overview of C-Therm Technologies and our core product line. I see a lot of familiar faces on the roster of participants, but I see some new faces too. Just taking a step back, who is C-Therm Technologies? What do we do? We're really a company that's been built around this idea of simplifying how to characterize thermal conductivity, how to make it more accessible as a measurement, how to make it possible to take these measurements under increasingly challenging environments or more representative application conditions. So today we really focus in on a really interesting area of that, which is in the high pressure work. But we've also worked in radiated environments in support of the nuclear field. We've worked in high moisture environments. We've done a lot of work with textiles where moisture matters a great deal. We've worked under different atmospheres, different gas conditions, high temperature. So really the sensor is an external sensor, has an advantage in being able to go into a lot of different types of environments and gives us a maximum flexibility. Of course, when we talk about that external sensor, we have some different options that you see represented. And we'll dive into these a little bit in more detail. At the left, you see a product called the Thermal Conductivity Kit. This is a very low-cost product offering. It's really oriented more around academic researchers, so folks that are perhaps limited budget, but looking to generate some thermal conductivity of solid materials or pastes or powders, and are really limited with a tight budget. So this kit lists for about $6,000. It's paired typically with a Keithley source measure unit and requires a laptop to put the kit together. Those are not included in the cost, but provides a really effective capability on a limited budget for measuring conductivity. In the middle, you see our core product, Trident. It's going to be the product that's featured most in today's work. This is a research grade instrument. It's a very powerful capability. It brings together the three most prominent methods in terms of transient techniques for measuring conductivity. It has the flexible TPS, it has the robust needle probe, and it has the high sensitivity, high accuracy, very versatile MTPS sensor. And it's the MTPS sensor, which stands for Modified Transient Plane Source, that you'll see featured inside of the high pressure cell that we offer. To the right, you see a product that's really more oriented towards the textile field, and that is the TX Touch Experience platform. This is for primarily characterizing the warm feel or cool touch of materials. I do see a few folks on the line from textiles looking to, I think, broaden a little bit their knowledge of other characterization tools outside of textiles. Great to have you online with us. Of course, the TX system is the one that we most often talk to folks in the textiles field about. And it's that, again, ability to characterize warm touch or cool feel as it relates to a material's performance. Okay, so in describing Trident, which is what we'll focus on mostly here, that's that product in the middle, we really describe the value as related to having the combination of those three methods, those three different thermal conductivity techniques that are very different, but very complementary in nature. And I really like this quote to explain that value proposition it presents by Abraham Maslow. Some of you will remember Maslow from your organizational behavior course back in university. But Maslow is quoted often, but one of the quotes I really like here is that when all you have is a hammer, everything looks like a nail. And I think we've been guilty in that past of sometimes having a bit of tunnel vision on the solution we were providing and not having the broader view of let's have some variety of tools available and be able to pick the best tool for the job at hand, because not every time is it requiring the hammer. Sometimes other tools are very beneficial as well. And that's the value of Trident, is bringing those three different techniques together. The flex transient plane source, that TPS method is more complicated to run, so it requires a better trained, more experienced operator or user, but it gives you a lot more control over the experimental parameters in running the measurement. So in adjusting test time, the power to the sensor, there are different size sensors available for the Flex TPS. So it's all about flexibility, the Flex TPS sensors. The needle probe, it's really all about robustness. This is a really strong sensor format. It's sheathed in stainless steel. It is primarily used for very sticky situations. So if you think of a polymer melt or some of those situations, where the sample may bond to the surface as you're testing it. The needle probe or transient line source, TLS, provides excellent robustness. And then the sensor we're going to focus on more here, and I'll detail further, is MTPS. This is a single-sided sensor. It's very novel in that it only requires access to one side of the sample. You have to cover the active area of the sensor, which is about 18 millimeters in diameter, but gives you incredible versatility in testing a wide range of materials. So these are the different sizes of the sensor. You see the MTPS, the TPS, and the TLS. The TLS is the longest. It's 150 millimeters. The TPS is available in some different size formats. And the MTPS is, as I mentioned, 18 millimeters in diameter. Some basic specs. The thermal conductivity range is broad for both MTPS and TPS. For the needle, it's a bit more reduced range, under 6 watts per meter Kelvin. There's the highest temperature range on the MTPS, up to 500 degrees C, depending on the application, and then up to 300 potentially with the TPS, and 200 with the needle probe. I think the rest of the specs you can kind of read for yourself. The most accurate and precise is generally the MTPS, followed by TPS, and then the needle probe, which is a little bit of a rougher measurement and is a trade-off for that robustness. There's a variety of industry standards referenced here across those different methods. And that's, speaks to, I think, part of the value of Trident, which is just having a diverse range of industry standards to be able to apply in your characterization of different materials. Not knowing always what tomorrow will bring to you in terms of testing requirements and new, novel, challenging samples. So because ARIA is going to reference quite extensively the application of the MTPS here, I wanted to explain a little bit further how it works. It is a one-sided interfacial measurement. The main part of the sensor is illustrated on the left, and you see this coil, and then around the coil is another ring. And those are comprised of two separate circuits. Both are electrically heated. The coil is heated electrically, and the circle that goes around it is heated electrically as well. The middle coil is the active sensor. So at the same time as we're heating it, we're monitoring the temperature change over time on that inner coil. The exterior guard ring or circle around the coil is used to ensure we get a one-dimensional heat flow into the sample material. Heat travels in the path of least resistance. The sensor is mounted on an insulative backing material. And with the use of the guard ring, this is a very innovative way to ensure we can test in a one-sided interfacial method. And that's why it's described as guard ring technology, MTPS guard ring technology. So the raw measurement itself is a voltage plot. It's the voltage plotted over the square root of time. Now, the voltage is just used as a calibrated way of measuring temperature. Okay, so the voltage drop is calibrated as a temperature change. So it's a lot easier to relate to this if you think of it as just a change time in terms of the measurement. The steeper that slope change in temperature, it's inversely related to the thermal conductivity of the material. So if I have a really steep rise in temperature change over time, it means that what's in contact with my sensor is a very insulating material. It has a very low thermal conductivity. If I have a very flat change in temperature over time, it means that my material is very conductive. I have something like a piece of copper, for example, a good heat sink material, a high thermal conductivity. So it's an inverse relationship between the temperature change over time and the effective thermal conductivity of the material in which we're testing. The thing that's really powerful about all this is we can do it in that one-sided interfacial way. It is done very quickly. The typical time parameter here is about 1 second in duration. If you compare that to steady state methods, we would be talking about typically in the order of an hour or more to come to stabilization. So being able to only have to have access to one side of the sample and being able to take multiple measurements in a very short period of time provides a nice advantage for this method in different applications where we want to better understand the true effective conductivity at different conditions, including being at elevated temperatures and pressure. The software provides, it's hard to make it out on this slide, but it provides a really nice graphical tabular format. So one of these columns is conductivity. You don't have to do any regression analysis with the MTPS method. It is basically point and click in terms of generating conductivity. You press start, it's going to start generating conductivity data for whatever's in contact with the sensor. So it is by far the easiest way to measure conductivity of the available methods, both in terms of what's available on Trident and more broadly speaking. We'll also record in that measurement the temperature at which the sensor is based, the thermal effusivity of the material. With effusivity, we can then derive other properties indirectly. So if you want to understand the heat capacity of your material, we can look at that indirectly based on the relationship between the effusivity and the conductivity of the material with an inputted density. Effusivity is the square root of the thermal conductivity, density, and heat capacity. So it can be used to leverage other thermal physical property data on your material. Okay, just before I pass this on, this is a close-up view of the high-pressure cell. Now, these can come in some different formats. So there are some different designs available depending on whether you're working with a solid or a liquid material, and the specs range a little bit based on those nuances. But this is essentially what it looks like. So inside, you can see the green chip. That's the active area of the sensor. The sample would be placed on top of this, the lid would go on top of it, and then you can pressurize the cell. You'll notice we equalize the pressure on the front surface of the sensor and the back surface of the sensor. And that's how we can achieve higher pressure conditions that would normally damage the sensor if we did not equalize that pressure. Okay, with that said, I'm going to pass this back to Arya. So I'll stop sharing here, Arya, and then I'll ask you to take control. But just before you go into your section, could I ask you to play the short video?
All right, so video. Yeah, this is a nice little overview of the Trident product itself.
Yesterday's thermal conductivity instruments typically limit characterization to a narrow range of sample materials. The samples are often forced to adapt to the instrument's rigid requirements, rather than the instrument adapting to the sample and application needs. Trident, by industry leader C-Therm, represents a new paradigm in thermal conductivity measurement, delivering 3 of the most powerful transient methods in one instrument. It's better to have options. Built on C-Therm's reputation for world-class thermal conductivity instruments, Trident is dynamic and satisfies the most prominent ASTM and ISO industry standards. It combines the precision of MTPS with the flexibility of TPS and the robustness of TLS, all in one modular package. These options support a wide range of applications without sacrificing ease of use. Trident meets the needs of today's labs and is future-proof for the challenges of tomorrow. The MTPS, Modified Transient Plane Source method, employs a single-sided sensor to directly measure the thermal conductivity and effusivity of materials. The method features the highest precision and sensitivity, providing accurate test results in seconds. It offers the maximum versatility for the non-destructive testing of solids, liquids, powders, and pastes. It is adaptable for high pressure, broad temperature ranges, and environmental conditions. No regression analysis is required. MTPS is the choice method for situations where reproducibility amongst multiple users matters. With a double-sided sensor available in different sizes, the Flex TPS Transient Plane Source method provides researchers the greatest flexibility over experimental parameters, including timing and power. It is recommended for more experienced users with specialty slab, anisotropy, and thin film modules available. With no contact agent required, the hot disk-style TPS sensor is ideally suited for polymers, compacted geological samples, metals, concrete, and asphalt. Flex TPS is ideal for experienced researchers looking to push the boundaries in thermal conductivity. Sheathed in stainless steel, the TLS, Transient Line Source Needle method, offers maximum robustness in thermal conductivity testing. TLS is best suited for granular materials, polymer melts, soils, slurries, and gels. C-Therm software provides full data acquisition and analysis in one user interface, allowing full control of all 3 methods. Intuitive, logical, easy. Trident reflects C-Therm's years of experience working exclusively to provide labs, researchers, and manufacturers with the very best in thermal conductivity measurement. C-Therm's products are globally distributed in over 65 countries around the world, with full local support. Trident. It's better to have options.
That's great. So that gives you some good visuals, I think, in terms of the system, and just a little bit better feel for what it's like to handle some of those sensors. Some really nice customer comments there as well, particularly like the one from 3M there at the end. But at this point, let's transition it over to Arya. Arya, if you're there, why don't you take the reins from here?
Thanks, Adam. Hey, everyone. So as Adam had mentioned, I'm going to kind of be going through a little more of like the application highlights. But before we get into that, I just want to give a little kind of background on some of these applications. So, applications where it matters, well, where it doesn't matter. For us today, Adam had mentioned, we will be focusing primarily on the oil and gas sectors, specifically having to do with the various extraction methods and some of the considerations that go into some of those processes and design optimization considerations. Also, though, it does have, kind of that one step removed from a lot of geological applications and many more. But again, mostly we'll be focused on the oil and gas sector. So just kind of going real high level here, when we talk about oil and gas or petroleum products, well, what are they and where do they come from? In essence, when we talk about petroleum gas products, that they're hydrocarbons. Typically you will refer to the liquid form as crude oil. You can refer to the solid form as bitumen. But overall, these are all petroleum-based products, and you're just kind of differentiating based on their state. But again, all just various forms of hydrocarbons. So as I mentioned, hydrocarbons, you can have different forms, whether they're in, their singular branch forms or alkanes, also referred to as paraffins. You can be looking at cycloalkanes or naphthenes. These are just similar to the alkanes, except obviously they're cyclically bound, typically having a higher boiling point than some of the branch structures. And also you'll find a small amount of your aromatic groups in there as well. But that's kind of a typical mixture that you'll see. There's also various contaminants or like various chemicals in there that aren't necessarily beneficial for you in your kind of refinement and extraction process, but they're just kind of tagged in there. You got like sulfur groups, nitrogens, and things of that sort. But really the significance of those different hydrocarbons in kind of the crude oil samples are what you can do with them after you've extracted. So when you go into a refinement process, so typically your shorter branch, your pentane to octane, compounds, these are what would be kind of fractioned out and turned into your gasoline that would be used in your everyday car. Some of the mid-range alkanes, they would be taken out into a fraction, and they're kind of used in your diesel fuel or your jet fuels and things of that sort. Lastly, the really big high molecular mass hydrocarbons, they can be refined into fuel oil, lubricating oil, or various even like asphalt. Lots of products come from the petroleum industry, but depending on what type of refinement that you're doing, you'll get different products out in the end of the process. So for us, we're going to relate some of these application notes to kind of the different types of deposits and different extraction methods that can occur. So just a few examples here on the left. You kind of have your basic your pump, which would be used to remove tight oil or shale oil. I have this picture in the middle of just kind of a rock that looks like it's burning. I have this here just to differentiate between shale oil and oil shale. Sometimes you'll hear those terms intermixed, but they're actually two very different things. So oil shale is a specific geological rock or a material that actually has a hydrocarbon source entrapped inside of it that needs to be removed, whereas shale oil is oil that's basically trapped inside or around a shale geological matrix or as such. Just a little differentiator there. And lastly, the oil sands or tar sands. Little picture there, kind of had a note. You actually have some of the largest deposits in the world located here in Canada, in the province of Alberta. But so just so you know, there's various different forms of where you would be looking to extract these resources from. So kind of talking about the shale oil deposits or your tight oil. You can see from this graphic here, it's essentially, as I mentioned, a oil that's basically entrapped inside of a geological formation. So basically, the extraction methods for these types of products are typically done via drilling or hydraulic fracturing, also referred to as fracking. And really, the depth of the deposit and the surrounding geological material, this is what really influences the parameters that are used in the extraction, whether that's the depth of the well, like how far in you have to go down, the increasing pressures that can occur at various depths, and things of that sort. The other one wanted to highlight here are oil sands or bituminous sands. These are it's different than your typical deposits, because whereas the other ones are in the earth and you have to extract it out, these are actually basically mixed in with various solid materials. So a typical deposit will be anywhere from about 10 to 20% bitumen, 5 to 10% water, and the remaining is the solid particulate matter. Extraction of oil sands, where possible, you can use surface mining techniques to remove basically the top portion, the easily accessible material. But when you have to deal with material that's found very deep down, you can't easily extract it. Steam-assisted gravity drainage, or SAGD, is kind of the method that's most prevalently used to obtain bitumen from oil sands. And in this case, it's obviously the formation that the deposit is around will matter, depending on the location that you're extracting from. But really, it's the intermix sample matrix that's really of interest here, and understanding the thermal properties of that mixture is what's really important when you're designing your extraction methods. And kind of bring this to relating it to the thermal properties. Well, why do they matter? In most industries, typically you'll fall into one of these two categories, and hopefully a little bit of both. But you have your cost, the reasoning, whether you're looking at your efficiency, so total recovery versus waste in your process. And then on the other side, there's the safety aspect. You want to make sure that these processes are done so the workers and people involved on these sites are doing so in a safe manner. And especially for the oil and gas industry, doing so in a kind of a globally safe manner, with respect to environmental concerns, and making sure that risks where they are minimized, and there's processes in place that help mitigate some of those risks. Just going to talk about a few of the extraction methods, kind of, again, pretty high level, but just kind of give you an idea if you weren't very familiar. But fracking, essentially, it's kind of in the name of fracturing. You're breaking down surrounding rock or geological material using a pressurized liquid. It gets a little more complex than that, but really at a high level, that's what the goal is. By doing so, you're able to the trapped product that you're looking to extract is able to basically be released and you're able to extract it. The graph over on the right kind of shows like an example of this, but it can get fairly complex depending on the depth of the location, the surrounding geological matrix, and things like that. But this technique has been around for quite a while now. I believe the first experimental studies were in 1947. A few years later, they began some actual some world in real world trials. And as of 2012, that information is now almost going on 10 years old. So there's probably been a few more since then. But 2.5 million frac jobs have been performed globally. So this isn't a method that's unknown or a lot of mystery behind it. But it's been around for a while, and it's a method that's used to extract the product of interest. Now, when you say fracking, some people you almost have like a negative connotation just hearing the word. A lot of people see that, and there are risks involved, as I mentioned. Some of the ones here, you could look at the surrounding matrix. You can have methane deposits, so you risk methane leakage. There's been some correlation showing that the breakdown in surrounding geological samples can increase seismic activity, and the process itself involves entering a pressurized water or a fluid into the system, and you have risk of wastewater contamination. But these are risks, again, that if you properly design these extraction methods, you can minimize these and almost mitigate them to a certain extent. And how you do that is through understanding what you're actually dealing with and how the process that you're introducing into the system will be changing its natural state. So one example, and especially in fracking, is you're introducing a massive pressure into your system, and to essentially fracture the surrounding matrix. So one way you can essentially look to see what's going to happen here is you can model the various geological formations based on your induced pressure to see kind of the size and location of where these fractures will be occurring, kind of looking at some of the thermal stress or thermal load that will be introduced into the system as well. Temperature is a parameter that can be very valuable in this type of method, and you can monitor it using actually there's been some work with these fiber optics. But essentially, if you're able to monitor the surrounding sample for various temperature rise or temperature change as the process is occurring, it gives you information on one, how much of the material is being extracted. You can see when that change occurs, you'll know when you're hitting your desired product. And also it can help again with the modeling of some of these methods to help really give you an idea of what's going to be happening before you actually go in there and do it. So your thermal properties here and fracking, they are quite valuable from both an efficiency standpoint and safety. Coming back to the oil sands, talking about the SAG-D method, again, kind of a very high level explanation here, but you have these various well bores that are dug into the ground, and essentially it involves the thermal manipulation of your matrix using steam injection. So as the steam is pumped into the system, it changes the thermophysical properties of the material. Also looking at the density change related to those thermal properties, by decreasing the viscosity of the material, it's more easily separatable and removable up to the surface via the other well. So typically these SAG-D methods, they're used where you can't access the surface for mining methods. Using the example of the oil sands in Alberta here, only about 20% of those are accessible via surface mining. So that means you're looking at 80% of this valuable resource that you have to use these processes for to get the product extracted. And just like another last little note relating the thermal considerations for oil sands, as I mentioned, the steam is your thermal input, which is what's used to drive the process here. But the effectiveness of the steam as a heating agent It really comes down to those thermal properties of the bitumen and the intermixed matrix that it's found inside. And again, the separation is driven by the density differences. So this graph on the right kind of helps illustrate kind of the point for someone who might not have actually seen bitumen before or handled it, but you can see in the top left there, in its kind of virgin reservoir conditions, or where it would be found in nature, very, very viscous, kind of, more so than peanut butter, if you can use that as an example. But as you see, through the manipulation of temperature, it begins to decrease to the far bottom right there, bitumen under sag D. So you can see the massive decrease in viscosity, which allows for much easier extraction of the sample. However, even still, you can see right at the 100-degree point there, typical oil in ground. So, the oil that you'd be recovering from like a tight oil deposit, still much less viscous than bitumen, even through these processes. So depending on what you're working with, you have to take into account the viscosity of these samples, how much thermal input is required to manipulate it to get it to the viscosity that you need it to be easily extractable, and things of that nature. And just one last slide here. I kind of mentioned early on there the different types of hydrocarbons and how you can take different materials out and different fractions for different processes. So this is just kind of a quick little illustration explaining that. So your crude oil will enter into a distillation setup essentially. This is a very simple example, but you basically, depending on the fraction of the volatility of the sample, they'll be coming out at different temperature points and being able to be used across a range of different applications. And again, this is essentially driven by the molecular mass differences of the various hydrocarbons. And again, removal of contaminants and such can also be done across these various steps to make sure your end product is pure and able to be used in its desired application. Just a note on bitumen too. Often bitumen itself is actually required to be upgraded prior to refinement itself. What that means is essentially it needs to go to basically a pre-processing step to help really remove some of those higher molecular mass materials and some of those contaminants and solid materials prior to actually being sent through to your typical crude oil refinement stations. Refineries are kind of typically classed as your kind of standard or heavy. Your heavy refinement stations can handle a certain amount of crude oil through various processes, but your typical ones may need basically a pre upgrade of the sample before it can reach that step. So that was just kind of your very quick and call it dirty highlight of some of the various applications and scenarios where this could come into play. These next slides will be going over some specific case examples, looking at different materials, whether it's solids or liquids involved in some of these processes, and kind of looking at the effects of either temperature, pressure, or both on the sample matrix and how it affects the thermal properties, specifically thermal conductivity, and how that can give you valuable information, whether it's for designing your processes, modeling, or even using them as almost a quality control methods to help screen the various materials that are coming off the various fractions or production lines. So this first one here, looking at the thermal conductivity as a function of temperature. This was done on a crude oil under a constant pressure. So again, just reiterating here, your crude oil contains a mixture of hydrocarbon compounds. An example where this could be, again, useful is if you sample at different stages along the refinement process, you can help monitor the efficiency, kind of what the value of the product that you're looking for is. If you can test the thermal conductivity of some of these samples, again, MTPS being very quick, 1 second test times, you can basically extrapolate whether, the process is working well, or if maybe there's something going on upstream that you have to go back and check and make sure everything is flowing. So the goals of the study was to assess if differences in thermal conductivity are found between the different samples, and to observe the effect of what temperature has on the materials themselves. So this was done on 2 different oil samples, again, under constant pressure. But what was found was there's essentially 2 different trends observed between the materials. Sample 1, seen in blue there, it had you could see at room temperature, at the low end of the temperature range, it had a kind of a lower thermal conductivity, which then increased initially with temperature. And then as the temperature profile continued, we saw a steady decrease. Sample 2, on the other hand, it started out, call it higher than sample 1, and then had a continuously, almost call it linear decrease with respect to temperature. So right there, you could say these 2 samples obviously exhibiting slight differences at the lower end, and then, offset most of the way through that temperature profile. But it can give you insight onto, all right, well, clearly these 2 samples were different. And if they were taken at different positions or sampled along different positions of your production line, it can kind of show you, it basically helps to highlight some of the differences that are obtained and give you information on what's actually inside of your sample prior to shipping it out the door. The next example here, we're looking at the thermal conductivity of a solid material under varying pressures. So, thermal conductivity of the solid material is, very important to your overall design, whether that's the geological matrix that's surrounding your oil deposit, whether you have to drill through that, or whether it's just going to basically be stimulated by your thermal load of the extraction process. Being able to help basically model that or quantify these values are very important. So again, the goal here was just to see the influence of pressure this time, different pressure across the same thermal profile. So testing here, so we see it was done at both ambient and 2000 PSI. So kind of no pressure at all versus some of the higher end of the high pressure cell capabilities. And again, this was done on a single sample across a similar profile, but just at different pressures. So what you can see here is between the 0 PSI and the 2000 PSI, initially you kind of see this offset. As you increase in temperature, the differences become somewhat more minimal, which is, that's very valuable information if you're dealing with kind of the lower end, and also it gives you information on what's happening if you do increase in temperature. But what we found was the thermal conductivity varied by, up to around 6% at the higher ends there. And this is, 6% just on a pure thermal conductivity measurement. That difference might not seem very like a lot, but if this is being used to help model different processes where you have to take your thermal conductivity into account and perhaps, include that in other calculations, your propagation of error in some of these calculations or measurements, that can become rather significant. So, being able to test in a more representative manner, even if it is 6%, that 6% can really mean a lot in some of these setups and some of these testing conditions that you'd be dealing with in the real world scenarios. This last highlight here, this is actually a study from, or basically it's a paper. We always like to, when we see our technology being used out in the real world, happy that people are actually using and getting great results, but it's basically a nice, pat on the shoulder for us to help be able to show it in its actual use. So this was out in the University of Stavanger in Norway, and they're doing an experimental study of temperature effects on the various materials used for well bores, basically to enhance the temperature profile for production wells and how you would model those types of processes. So this kind of paraphrasing from the journal itself, but in a well bore, the thermophysical properties are used to construct and of the surrounding matrix play a major role in the heat exchange processes. The information is important to quantify, as you can basically develop one, you get the highest level of safety, and you can also do that at the lowest cost. So it's, again, that trade-off, or not trade-off per se, but having that ability to, one, save money, but also do so in a safe manner. So the results that they obtained were used to help model a wellbore, such as one seen here. Basically, there you have your different levels with different levels of casings and different thicknesses of materials and surrounding different material types involved in the process. So these can get rather complex very quickly. So being able to really, get that quality data to model the processes, it's really invaluable. So with a single sensor, just with the MTPS, they were able to test 3 different things for thermal conductivity. The product of interest on the left here, so they were able to look at the oil sample itself, the construction material of the wellbore, so looking at the various grades of stainless steel. And 3, they're able to look at the surrounding geological matrix, so various types of geological samples. And I thought that was, it's great because in the entire paper, they're able to use one sensor to test 3 completely different material types. And when you're in a research setting, trying to get these numbers, being able to use a single sensor or a single setup to do all these different testing really helps eliminate some of those variables as to you're testing, your liquids with one setup or one method and then swapping to another method to do this. It really just helps keep everything under kind of one roof and very consistent from a testing setup standpoint. So in conclusion, just kind of wrapping up some of the key points there, but your thermal properties, they can give you very important information, whether that's in the design from a safety standpoint or whether it's looking at a financial sense. The capability to test materials involved in your system, whether that's the liquid sample, your solids, or the various types of solids that might be involved. It's really a great tool to be able to do this because you can get your results and you have them with confidence, and you're able to use those values and really help model some of these processes with representative conditions, and that's really just invaluable for some of these applications where those tiny differences in results will affect the overall design and efficiencies. So I'm at this point, Adam, I'd throw this back to you for any concluding remarks you have. Just wanted to put this up here as some upcoming webinars. You can check these out here. Again, also all these webinars that we do record are available on our website. Any comments there, Adam?
Yeah, great job, Arya. I think that was an excellent overview of some of the application data generated with the high pressure cell. Some great background in terms of the context of why it matters, particularly as we calculate the energy required for some of these extraction processes and the subsequent processing of the material. So well done. Yes, we do have a number of upcoming webinars that may be of interest to some of the participants on the line. The dates are just being finalized, but I'll just give you the topics, maybe something to keep an eye out for. We have one that's going to be focusing on the thermal conductivity characterization of powders, and it'll speak to a variety of different applications of the MTPS sensor technology. But one of the main ones is in additive manufacturing, particularly in metal additive manufacturing, as well as metal injection molding. We'll be looking at the thermal property characterization for its inherent value in modeling some of those processes and optimizing some of those processes. We'll also be looking at it as it relates to understanding the consistency in the processing, blending, homogenizing of some of the metal powder blends in preparation for injection molding with metal powders. So that's one webinar that's coming up that may be of interest to some of you on the line. The other one is a closer look at the uses for the TC kit. Remember at the beginning I mentioned the kit is really oriented more for those of you that might be on a really limited budget. So typically more of an academic researcher that's looking to generate some basic test data sets, perhaps incorporating it even into coursework or lab work, experiential learning for your students, and generating conductivity. So we'll just provide a little bit of an overview there of some of the applications you can accomplish with the kit, and an overview of how it works in greater detail. So if you're interested in either of those topics, please let us know. I'd be happy to follow up with you with further details, but you'll probably also see a notice go out when those dates have been scheduled within the next few weeks. I did also want to just mention we do have a special promo running. I don't know if anyone would be interested in it, but it's a really good deal that we put together with our partners over at C-Therm Instrumentation. We represent C-Therm here in Canada, and we put together a special package with them. It combines a DSC, a set-line DSC, and a C-Therm TCI, thermal conductivity system, for under 45K USD. That's an incredible deal for anybody that's in the market for those capabilities. Really a great package in developing a lab for broader thermal analysis, bringing both DSC and thermal conductivity capability in at that price point. If you're in the US, as most of you are on the line, we are working with them and also bringing this offer to the US. So if it is of interest, maybe just send us a short email, and we'd be happy to follow up with you one-on-one with that offer. Lastly, we have reserved some time for a Q&A session. So I think what we'll do here, Arya, is we'll probably stop the recording at this stage, and then we'll open it up for a Q&A session if you're okay to stay on the line.
That works with me. I'll quit the recording right now.